So we're going to start off by going over question one on the CS 186 midterm from spring 2021. Um, the first question is a true or false question. It's asking us to mark which statements are true. So the first choice, all paths from the root of a B plus tree to a leaf node will always pass through the same number of inner nodes. This is true. It's a property of B plus trees. A B plus tree is always balanced, so it always takes the same number of IOs to get from the root to a leaf. The next choice, clustered alternate 3 B plus trees are always at least as efficient as clustered alternate 2 B plus trees in terms of IO cost. Recall that what alternate 3 B plus trees have is it has a list of data values that are stored in the data pages. And so if there's one matching record, then it's equally efficient as alternate 2. And if there's more than one matching record, it's more efficient. So this is also true. The third choice, a B plus tree with height h and fan out d will always have more than 2d times 2d plus 1 to the power h minus 1 keys. This is typically the formula, or this is a variant of the formula that we use for the max number of keys and not the minimum number of keys. One easy way of thinking about this is you can actually delete keys and this formula will not hold. But also it's worth drawing out an example. I can draw one out real quick. So if you have one node, root node, and then two leaf nodes. And this leaf node is populated, and this leaf node is populated. This formula will not hold. So let me try that out. Having an index on a table makes inserts more efficient than inserts into a standard heap file. Well, inserts into a standard heap file are very efficient. You can just get the last value or the last page, and you can insert into that page and write it back. Inserting into a table means populating or potentially splitting nodes, bubbling up the keys, and so this is potentially less efficient. Okay, alternate 2 B plus trees are useful for frequent full scans of the relation. This is also not true. If you're doing frequent full scans, then having a heap file is good enough. If you have to do a frequent full scan with an index, you'd have to work your way all the way from the top or just not use the index. Deleting a value from a B plus tree deletes it from any inner nodes it may be in as well. While this is false as well, recall that deleting a value only deletes the key. You don't delete any of the inner nodes. So that's it for part A. Part B. So we're given this table orders, and we have a few different. We have a key SID, and then we have CID, order, and store ID. And we have a few different indices given to us. So we have index A, which is an alternative 2 index, an SID. We have index B, which is an alternative 3 index on store ID. And we have index C, which is an alternative 3 unclustered index on CID. We don't have anything on order, so that's worth noting. And we're also given some additional assumptions about the table. So the first question is asking us what's the maximum number of keys index A can hold. So we can see that index A has a height h of 2 and d of 4. So we can look at the formula for what's the maximum number of keys something can hold. It's 2d times 2d plus 1 to the power h. And so if we see d is 4, so 2d is 8, and 2d plus 1 is 9, and h is 2. So the answer is 648. Okay, the next question is asking us to calculate the minimum possible IOs for the following query. And we're selecting from orders where order is equal to jasmine milk tea. Well, recall that we don't have a B plus tree built on order. So we're going to have to do a full scan. So we do a full scan of all the pages, and the orders table has 100 data pages, so we just do 100 IOs. Okay, now calculate the minimum IO cost for the following query. Select from orders where CID is equal to 50. Okay, so now we do have a B plus tree on CID. The height is 3, which means that to read the index node and all the inner nodes, it takes 3 IOs. Then we read the leaf node, which takes an extra IO, and then we read the data page, which takes another IO. So in total, we have 5 IOs, 3 for the inner nodes, 1 for the leaf node, and 1 for the relevant data page. Okay, this question is slightly more tricky. It's saying select everything from orders where CID is equal to 100 and SID is greater than or equal to 600. So we have 2 different indices. We have one on CID, one on SID. I'll walk through one of them and I'll leave it as an exercise for you to go through the other. But the more efficient one to go through is SID. So if we see the first record for where SID is greater than or equal to 100 appears on the 70th leaf node. And this in total has, this B plus tree in total has 80 leaf nodes. So if we scan down to the 70th leaf node and then we scan the remaining leaf nodes, we would have scanned 2 inner nodes. So since the height is 2, then we'll scan 11 leaf nodes. And then the question is, how many data pages do we scan? So this is an alternative to clustered B plus tree. So we have in total 88 keys that we need to check. So we have 11 leaf nodes, and then we have 8 keys per node. So we have in total 88 keys that we need to check. How many data pages does this occupy? Well, we can see that there's 20 records per page. And this leads to a total of 5 data pages. So in total, we'd have 2 inner nodes, 11 leaf nodes, and 5 data pages. We get the 20 records from here. Okay, if we wanted to do a range scan on store ID and find out how many orders we had at locations with store ID is greater than or equal to 2, which index do we use? Well, so if we look at index B over here, it's an unclustered index. So the problem with an unclustered index is you're going to have to read every data page after you read the leaf node. And so this makes it very, very inconvenient because you read the leaf node and then you read a data page, and then you read the next record in the leaf node, and then you read a different data page. So this is very inefficient. So it makes most sense to do a full scan here. Okay, the next question is about bulk loading. So we want to reconstruct index A. So we have a B plus tree on SID with D is equal to 4. And we have orders which contains 900 records with a fill factor of 0.75. So how many leaf nodes would this reconstructed tree have? Well, we have a fill factor of 0.75. That's worth noting. And how many records can each leaf node hold? Well, since D is equal to 4, it can hold a maximum of 8 2D. And so in practice, we only hold 6, right? Because 8 times 0.75 is 6. And so since we have a total of 900 records, if we divide 900 by 6, we get 150 leaf nodes. Okay, the next question is asking us what's the minimum height of the reconstructed tree. And what the approach the solutions took was it took a form of trial and error. So if you plug in the formula 2D times 2D plus 1 to the h, you'll find out the number of records that you can hold. And recall that there's some amount of constraining based since bulk loading doesn't hold all the records. So if you plug in h is equal to 2, you'll find that you can store at max 486 records, 2D times 2D plus 1 plus 2D times 2D plus 1 plus h. And if you plug in h is 3, you'll get 8 times 729, which is a significantly higher value. So the answer is the minimum height must be 3.